This lesson discusses another major topic, which is rational functions. In previous lessons, we have looked at polynomial functions exclusively. And what a rational function is taking that then sort of almost to the next level. A rational function is any function of the form n of x over d of x, where n of x is a polynomial of a certain degree and d of x is a polynomial of a certain degree. So when we were looking at polynomials before, we were basically looking at one component of what now is a rational function. Now this polynomial in the numerator can really be any polynomial, and this polynomial in the denominator can be any polynomial. That'll affect the rational function, but generally a rational function is comprised of polynomials. In this case, we're dividing them. If we're dividing them, then certain issues arise that didn't arise when we were looking at a single polynomial. One major thing that's an issue is domain. When you look at domain, you want to look for all the values for the variable that can be plugged in that make the function defined. This is a fraction. So a fraction will be undefined when the denominator is equal to 0. That's when it's undefined. So the domain are all the values so that the denominator isn't 0. But oftentimes to figure out where the denominator is not equal to 0, it's easier to say, where is it equal to 0? Okay, now I want everything else. So a very simple one would be, say, this function right here. F of x equals 1 over x. This function is the simplest rational function you could possibly deal with. It gets across a lot of the major points that come up with rational functions, but again, this is sort of the simplest one you can do because the numerator and denominator are really the simplest polynomials possible, 1 over x. So if I want to find the domain for this function, I want to find all the values for which the denominator is not equal to 0. Well, the domain is going to be all x such that x doesn't equal 0, right? The denominator is x, and I don't want that to be 0, so I don't want x to be 0. I could write that in interval notation, and I could say negative infinity to 0, union 0 to positive infinity. There's lots of different ways to write domain. But anyway, you should just be able to at least look at this function and realize which x's can you not use. So I will not be able to use an x value of 0. Any other x value, when I plug it in, I'll get an answer, but an x value of 0 just does not work. What that means is that if I use an x value of 0, I'm not going to have a point that goes along with that x value because there is no y value. So when I go to look at my graph, x-axis, y-axis, for the x value of 0, okay, which is right there, there's not going to be a point. So what happens is there's going to be a break in the graph right here at the y-axis. And that's something majorly different than what was happening with a lot of our polynomial functions. Really, all of our polynomial functions were continuous. And that's one thing we talked about in the very beginning of polynomial functions with their graphs, is that a polynomial is always continuous over its entire graph. It's all one solid piece. The domain for polynomial functions was all real numbers. However, now these functions, rational functions, the domain may not be all real numbers. In that case, we're going to have breaks in our graph. We're going to have values that we have to eliminate from our domain. So let's start to look at what this graph looks like. And we don't have to do anything major to put this graph together. We can just sort of look at plotting points and developing our graph from that. We'll have better ways of drawing the graph later. But right now we're just looking at, say, let's plug some x values into this function and see what we get. So let me say an x value of 1. If I use an x value of 1 and I plug it into this function, I'll get a y value of 1, because 1 over 1 is 1. So that point's on my graph. As I start plugging in bigger and bigger and bigger x values, let's say 10, or even 100, or even 1,000, what's going to happen? Well, I'm going to plug them in here for x, and I'm going to get 1 over 10, which is a fairly small number, right? The y value is 1 over 10. If I plug in 100, I get 1 over 100, even smaller. 1 over 1,000 is going to be this one. So my y values are getting smaller and smaller and smaller. Okay? If I plugged in some ridiculously large x value, close to positive infinity, I would get 1 over that value, which would still be a positive value, but really close to 0. So what happens is this graph, as it moves this way, keeps getting closer and closer and closer to the x-axis, closer to a y value of 0. But it's never going to get to that y value of 0. That's going to be something, so we'll talk about in a second. Let's look at these x values. As x values get closer and closer and closer to that break point, that 0 point, I'm going to be plugging in values like a half, or a third, or so on. Well, if I plug those in for x, if I plug a half in for x, I'm going to get 1 over a half. Well, if I divide by a fraction, I flip and multiply, and that gives me 2. So this x value gives me a y value of 2. Same thing for a third, I'm going to get 3, and so on. And as I get close to 0, I can get really close to 0, my fraction is going to keep flipping over, which is going to give me a bigger and bigger value. So as I get closer and closer to that break, my graph keeps getting bigger and bigger, going up to positive infinity. Alright, that's going to be something, we're going to call that a name. We look at it on the other side. Let's try -1. Plug -1 in, I get -1. So I get this point. Generally the same thing's going to happen over here. As x gets closer and closer to negative infinity, right, my y value is going to be negative but really close to 0, and same thing in the opposite direction. As I get close to 0, same thing's going to happen but just negative, so now it points down. So this is what my graph looks like for 1 over x. Now what happens here is there's two things that really happen quite often with rational functions. There's this break in the graph here, and this break in the graph really affects my graph pretty much very drastically. If you look at it, as my graph approaches that break, my graph goes up to positive infinity, and on this side goes down to negative infinity. I can't cross over that break because it's a break in the graph, and it also bends my graph completely up or completely down as I get close to that break. Think of this breaking point in the middle here like it's a wall, and as my graph is traveling closer to that wall, it has to veer off on either side. One side goes up, one side goes down, and whether it goes up or down is dependent on the function, but the idea is it can't cross that line and it veers off. Also, if you look at what happens on the ends of the graph, down here and down here, as I'm going closer and closer to an x value of positive infinity or an x value of negative infinity, my y values aren't pointing up or pointing down. When we did polynomial functions, we would get a graph that looked like this. In that case, on one end I pointed up, and one end I pointed down. So y was going to positive or negative infinity. That's not happening here for this graph. On this graph, if I look at either ends, my graph as x goes to negative infinity, y is not going to positive or negative infinity. Y is getting closer and closer to 0. And the same thing on the other end. As x goes to positive infinity, y is not going to positive or negative infinity like it would be here. Y is going to 0. So we call that a horizontal asymptote. And this one in the middle we call a vertical asymptote. So we have to define those two things. So we want to define these asymptotes. First, horizontal asymptote. Some horizontal line y equals b will be considered a horizontal asymptote of the graph of f of x if f of x approaches some constant value b as x goes to positive or negative infinity. The easiest way to think about this is if on the ends of your graph your y values are getting closer and closer to a constant value b, then that constant value is considered to be a horizontal asymptote. However, if at the ends of your graph is just pointing up or pointing down, going to positive or negative infinity, you know, both up, both down, we've done all sorts of things, then you don't have a horizontal asymptote because your y value, your f of x value, is not approaching a constant. Only if your y value is approaching a constant at the ends of the graph. That's what this means here, the ends of the graph. Then you would have a horizontal asymptote. So an example would be something like this. I have some graph, and my graph on either end there's this horizontal line, and on the ends my graph approaches that line. Okay? That would be a horizontal asymptote. Some functions have the same horizontal asymptote on either side. Some don't. Rational functions, if there is going to be a horizontal asymptote, you'll have the same one on both sides. You know, I could have a function that looks like this, where on one side, down here, I approach this horizontal line, and on the other side here, I approach this horizontal line. That's not going to happen with these rational functions. That's other functions can have a horizontal asymptote on one end or the other end, but rational functions, if they have a horizontal asymptote, it'll be on both sides. All right, then we want to talk about vertical asymptote. So the line x equals a, which is the way you write a vertical line. Remember, y equals b is the way you write a horizontal line, b being just a number. X equals a is the way you write a vertical line. Again, a being just a number. So the line x equals a is a vertical asymptote of the graph of f of x if f of x approaches negative infinity or positive infinity as x approaches a. It sort of looks like this definition is the reverse of the previous definition, and it kind of is. So if you think about a graph, there's some vertical line. Okay, here's some vertical line with an x value of a. Right, so the equation of that vertical line is x equals a. If f of x, that's your y value, goes to positive or negative infinity as you get close to that vertical line, we call that vertical line a vertical asymptote. So as my graph gets closer to that vertical line, if my graph goes up to positive infinity or down to negative infinity, okay, that vertical line we call a vertical asymptote. And on this side, it could do the same thing. They could both go up. Both sides here could go down, one side up, one side down. I mean, that all depends on the function, but the idea is as I get closer and closer to this vertical line, my graph goes up or goes down, then that line is considered to be a vertical asymptote. Y goes to positive or negative infinity as x gets closer and closer to that line. So here are three examples of three different rational functions. And different things happen with these rational functions, but they all are somewhat related to horizontal and vertical asymptotes. Not every rational function is going to have a horizontal and vertical asymptotes. Some might have vertical, not horizontal. Some might have horizontal, not vertical. But most rational functions will have at least a vertical or a horizontal, usually at least one of each. So let's look at this first function here. Okay. F of x equals 2x plus 1 over x plus 1. Now we're going to learn how to come up with this graph, but if you look at this graph here, right, this graph is going to go up this way, it's going out this way, so on. Right, there should be arrows on the end here. And you have this vertical line, and as my graph gets closer to that vertical line, it shoots up to positive infinity and shoots down to negative infinity here and here, which tells me that this is my vertical asymptote, and it's at x equals negative 1. Also, if you look at the ends of the graph, on the ends of the graph, my graph is approaching this horizontal line at 2. So that means I have a horizontal asymptote at y equals 2. Okay. So look at this next graph here. F of x equals 4 over x plus 1, x squared plus 1. Now there is no vertical line that I'm getting close to that makes my graph shoot up to positive negative infinity. So there is no vertical asymptote. Okay. However, if you look at the ends of the graph here, on this end and on this end, it's getting closer and closer to the x-axis. X-axis being that horizontal line. So this is my horizontal asymptote. Y equals 0 is another way of writing the x-axis. Okay. So this one has a horizontal asymptote, no vertical. So then go to the next one. Okay. Here's a vertical line. And as my graph gets closer to that vertical line, it's shooting up to positive infinity. Now this one's going to positive infinity on both sides. The first one went to positive infinity on one side and negative infinity on the other side. But this one's positive infinity on both sides. And that's just because it's a different function. Every function behaves differently. But if it approaches a vertical asymptote, it either has to go up or go down as it gets closer to it. So that's happening here. So this line right here is a vertical asymptote. That has an x value of 1. Look at the ends. The end of the graph here, the end of the graph here. Again, I'm getting closer and closer to the x-axis on either end, so I have a horizontal asymptote at y equals 0. So here's some things that go on with rational functions. Again, we're going to have to learn how we come up with these asymptotes, how you find a horizontal asymptote, how you find a vertical asymptote, and then also how we put these graphs together. But now you have a general understanding of some major pieces that go into graphing rational functions. And a lot of this has to do with that fact that these domains are no longer all real numbers all the time. If we have a domain that's restricted, a restricted domain essentially creates breaks in your graph. And if you create a break in the graph, you're going to create these segmented graphs where they're in separate pieces. Also, the fact that this is defined by a fraction creates these horizontal asymptotes as well. So we're going to have to look at that in a little bit closer now. So now we want to talk about finding these asymptotes. How we can look at a rational function and figure out where's the vertical asymptote if it has any, where's the horizontal asymptote if it has any. So let's look at a rational function. So a typical rational function will have this form, this setup. Polynomial over polynomial. A common thing that you look at when it comes to these is that you want these two polynomials, the numerator and denominator, to not have any common factors. Now, if they do have common factors, there's a way you deal with that, and largely you cancel the common factors, and that would have some consequence when it comes to the graph. But to keep this as simple as possible when we first start doing these, we're going to say, let's look at the rational functions such that the numerator and denominator don't have any common factors. So that means basically that this fraction that we're looking at right here is simplified as much as possible. Alright, so if that's the case, if my numerator and denominator have no common factors, again, we'll come back to what happens if they do have common factors at the end of this lesson. But let's look at if they have no common factors. Then the graph of f of x will have vertical asymptotes when the denominator is 0. And that's it. Well, the denominator is a polynomial. So essentially what you have to do is find zeros of this polynomial. Those zeros will be the vertical asymptotes, but only if they have no common factors. Here's the thing. If n of x and d of x do have common factors, then where the denominator is 0 may not only be vertical asymptotes. That denominator may contain vertical asymptotes as well as something that we consider to be a hole in the graph. Okay? So that has to do when there are common factors. So we're going to ignore this situation for right now, where what if the numerator and denominator do have common factors? If the numerator and denominator do have common factors, finding the vertical asymptote has an extra step to it. But for right now, if n of x and d of x have no common factors, all you have to do is find the zeros of the denominator. So look at this particular example here. F of x equals 2x over 3x squared plus 1. So I want to find the vertical asymptotes, if I can, of this function. Well, first of all, I can't factor the numerator or denominator anymore. So therefore, there are no common factors. So it's the situation we want to look at right now. So all I have to do to find the vertical asymptote is to figure out where is this denominator equal to 0. Well, actually it's never equal to 0, because if I try and solve this equation, I get 3x squared equals negative 1, x squared equals negative 1/3, and right now I have a square equals a negative number. The only way I can do that is if I talk about imaginary numbers, and sort of from the start of this whole thing, when we started with polynomials, we said we're going to assume imaginary numbers don't exist. So for right now, essentially what we could say is in the real number system there's no solution, right? And if there's no solution to this equation, then there's no vertical asymptote, because really there's no place where the denominator is 0. Let's go to the next one. 2x squared over x squared minus 1. First of all, can the numerator be factored anymore? No. Can the denominator? Yes. But factoring that denominator doesn't cancel anything in the numerator. So therefore it's simplified as much as possible. Again, what we want, there's no common factors. So then what do I say? Alright, I want to find the vertical asymptotes. Let's let this denominator equal 0. Well, that denominator, since I can factor it as x minus 1, x plus 1, will equal 0 when x equals plus or minus 1. So when x equals plus or minus 1, those are the zeros of the denominator. Those are my vertical asymptotes. Okay? And there's two of them, right? One line is x equals 1, and one line is x equals negative 1. Those are two vertical lines. Those vertical lines are my vertical asymptotes. Let's go one more. Again, I can't factor the numerator, I can't factor the denominator, it's simplified. I set my denominator equal to 0. That's going to be my vertical asymptote. So the denominator will be equal to 0 when x equals 0. This is my vertical asymptote for this particular function. So that's all you have to do to find vertical asymptotes. A key, again, is this right here. There's no common factors to start. If there are common factors to start, again, we'll talk about that at the end of this lesson, but generally, just to introduce it right now, is you would have to cancel those common factors and then find where the denominator is 0. We'll get those examples in at the end. If I want to find a horizontal asymptote, okay, there are steps that I can follow there too. Now, it has nothing really to do with the zeros. Right, to find the vertical asymptotes, we're looking at the zeros of the numerator and denominator, or sorry, just the denominator. For horizontal asymptote, we're not looking for zeros, but what we still want to do, just to make this as simple as possible, we want n of x and d of x to have no common factors. Once we determine that they have no common factors, what I'm going to do is look at not the zeros, but I'm going to look at the degree of the numerator and denominator. The degree is the highest power for each polynomial. In this case, the degree here is going to be n, and the degree here is going to be m. So if I look at these two degrees, this is the degree of the numerator, this is the degree of the denominator. I look at those degrees, and how those degrees compare to one another is going to determine if I have a horizontal asymptote and what it is. So first scenario, n is less than m, meaning the degree of the numerator is less than the degree of the denominator. If you ever have that, then your horizontal asymptote will be y equals 0. Next case, n is equal to m. So the degrees in the numerator is equal to the degree in the denominator. Well, if that happens, you're going to have a horizontal asymptote. That horizontal asymptote will be a sub n over b sub m. Well, what are those things? Those two things right there, a and b, are these leading coefficients. So what I'll have to do is I'll divide these leading coefficients in front of these x to the highest powers. That division right there is going to be my horizontal asymptote. Okay. Third scenario, n is bigger than m. Again, the degree of the numerator is bigger than the degree of the denominator. In that case, there's not going to be a horizontal asymptote. Alright? So all you have to do is look at the degrees. Once you look at the degrees, you know these three scenarios, and you'll determine your horizontal asymptote from there. So let's look at this first one again. F of x, 2x over 3x squared plus 1. Again, we said it's already simplified. These three examples here are the same three examples we just looked at. So it's simplified as much as possible. The degree of the numerator is 1 over the degree of the denominator is 2. So in this case, the denominator is bigger. Right? If the denominator is bigger, that's your m. M is bigger. I have the first scenario, so y equals 0 is the horizontal asymptote. Okay? Next one, the degree of the numerator is 2, the degree of the denominator is 2. They're the same. If the degrees are the same, n equals m, I have to divide the leading coefficients. Well, if I look at the leading coefficients here, 2 is the leading coefficient here, and there's really a 1 in front of this one. So if I divide those two things, because the degrees are the same, y equals 2 over 1, or 2, is the horizontal asymptote. Okay. Last one. 2, 1. The degree of the numerator is bigger. If the degree of the numerator is bigger, there's no horizontal asymptote. So in this case, there's no horizontal asymptote. So you can see how you find these horizontal asymptotes and how you find these vertical asymptotes. Vertical asymptotes, you look at the zeros of the denominator. Horizontal asymptotes, you look at the degrees of the numerator and denominator, and that dictates where your horizontal asymptote, if you're even going to have one, will be. So you're going to have to get used to doing these and following some of the examples. So the next thing we're going to need to do is to start looking at putting these graphs together. We have a lot of the components we need to be able to do that. Now we just got to all fit it together. So we're looking at a rational function, n of x over d of x, each one being a polynomial. Those polynomials, again, we want to make sure they have no common factors. If they do, again, I'll tell you that later at the end of this video. But for right now, what do we want to do? We want to follow these 6 steps for the most part. In these 6 steps, you're going to first do the 2 major things you need to do. Find the vertical asymptotes and find the horizontal asymptotes. So that's the first 2 steps. How do you find the vertical asymptotes? Let the denominator equal 0. How do you find the horizontal asymptotes? Well, you're going to check the degrees of the numerator and denominator, and that's going to tell you what your horizontal asymptote is. Next things you're going to want to do is to start to get some idea of where your graph is located. So what we want to do is find the x and y intercepts. So step 3 and 4 are all about finding the x and y intercepts. How do you find a y-intercept? I find a y-intercept by letting x be 0. So essentially find f of 0. How do you find an x-intercept? Well, you let y equal 0. Well, these things are fractions, and the only time a fraction will be equal to 0, okay, we're looking at this fraction. If I want to set this whole fraction, n of x over d of x, equal to 0, the only time that's going to be equal to 0 is really solely when the numerator equals 0. So if I want to find the x-intercepts, all I really have to do to find the x-intercepts is let the numerator equal to 0. Now don't confuse that with finding where the denominator equals 0. That means 2 different things. Denominator equals 0 is going to be your vertical asymptotes. Numerator equals 0 is going to be your x-intercepts. And all this is all on the premise that there are no common factors. Next, once you have that, you have a general idea of where your graph is kind of set up in your location. So you're going to probably need to plot a couple of checkpoints to get a better idea of where your graph is located. Once you determine that, sort of complete your graph with some smooth curves and approach your asymptotes, vertical and horizontal, and you got your graph. Okay, so these are the 6 steps you go through. A lot of them are fairly close to what we were doing with polynomials. I mean, think about it. Polynomials, we did x-intercepts, y-intercepts, and we plotted checkpoints. The first 2 steps are the major differences because we never had these asymptotes with polynomials, but these are real defining factors of rational function graphs. So number 1, let's look at graphing this rational function, fairly basic one. So first thing I want to do, I want to find my vertical asymptote. Okay? This fraction is simplified as much as possible, right? You can't factor the numerator and denominator anymore, and nothing can cancel. So all I have to do is say x minus 2 equals 0. That will be when x equals 2. There's my vertical asymptote. Second thing I want to do is find my horizontal asymptote. Well, the degree of the numerator, since there is no x there, is going to be 0. The degree of the denominator is going to be 1. If the degree in the denominator is bigger, then y equals 0 will be my horizontal asymptote. Third thing, find your y-intercept. So what I need to do is find f of 0. Well, if I find f of 0, I get 3 over 0 minus 2, which gives me negative 3/2. So there's my y-intercept. So here's my horizontal asymptote, here's my y-intercept. Step 4, x-intercept. X-intercept, I have to set the whole function equal to 0. But since this function is a rational function, all I really have to do to find when 3x minus 2 equals 0 is set the numerator equal to 0. But that numerator is 3. It's never going to be 0. So then there's just no x-intercepts. Alright, so what do we know? We have a vertical asymptote, we have a horizontal asymptote, we have a y-intercept, and no x-intercepts. So this is the stage where you start to really put that graph together. Alright, so vertical asymptote, x equals 2. So here's my vertical asymptote. I'll denote this by a dotted line. Dotted line because this isn't actually part of my graph. My graph will be denoted by a solid line. Y equals 0 is my horizontal asymptote. That's the x-axis. I have a y-intercept at negative 3/2. So here's negative 1, here's negative 2, here's negative 3/2. Alright. So now we have to start putting our graph together. Now this is where plot your checkpoints are going to come in. You plot checkpoints based off of trying to figure out where your graph is located. Well, we can actually start putting our graph together before we do those checkpoints. My graph goes through this point. I also know that I have a vertical and horizontal asymptote. And as my graph moves along, it has to approach those vertical and horizontal asymptotes. So the idea is at the end of the graph over here, my graph has to approach this horizontal asymptote. Also, as I get closer and closer to this vertical asymptote, my graph has to either go up to positive infinity or down to negative infinity. Well, going up to positive infinity actually isn't an option, because my graph would have to cross the x-axis in order to do that. But there are no x-intercepts. So if I can't go up, I have to have my graph go down. So that's what my graph does there. And that's all just by knowing this one point that was on my graph and that I have these vertical and horizontal asymptotes. Now, here's where I need a checkpoint. I have no idea what's happening on this side of the graph. So I need to figure out where my graph is located before I can start doing the same things I did on the other side. So what I'm going to do is I'm going to take some value over here, let's say 3, and I'm going to put that into my function. So I'm going to find some checkpoints, and that's basically going to find f of 3. Which is going to be 3 over 3 minus 2, which is 3 over 1, or 3. Which tells me that 3, 3 is a point on my graph. So that's up here. Once I determine that my graph is located up there, I say that that's the only option for my graph. Okay. In that, if I'm going to have to approach the vertical asymptote, I can either go up or go down. Well, down isn't an option because it would cross the x-axis. We can't do that. There are no x-intercepts. So up is the only option. And on the other end, here, going the other way, I have to approach this horizontal asymptote. So that's what it's going to have to do. So this is what my graph looks like. Alright, here's another one. So we're going to sketch the graph of this particular function. Again, if you look at this numerator and denominator here, there's no common factors. I can't factor the top or bottom anymore. Nothing will cancel. This is my function. Simplified as much as possible. So first step, vertical asymptote. Okay? So if I want to find the vertical asymptote, I set the denominator equal to 0. That's it. There's my vertical asymptote. Second step, horizontal asymptote. Look at the degrees. The degree in the numerator and the degree in the denominator are both 1s. So if the degrees are equal, I have to divide the leading coefficients. In that case, it's 2 over 1. So my horizontal asymptote is y equals 2. Okay? Again, the vertical asymptote is a vertical line. You should write it as x equals a number. Horizontal asymptote is a horizontal line. You should write it as y equals a number. Don't just write 0 or 2 usually. You should know that this is how you write vertical and horizontal lines. And these are vertical and horizontal lines. Step 3, y-intercept. Find this f of 0. So in that case, let me see that function a little bit better. In that case, I'm going to get 2 times 0 minus 1 over 0. Well, that can't happen, right? I can't have 0 in the denominator. Remember, that's where my vertical asymptote was. So there is no y-intercept. Okay. And step 4, x-intercept. So I'm trying to find my x-intercept. I have to set my function equal to 0. But remember, since this is a fraction, you really only have to set your numerator equal to 0. So that gives me x equals 1/2. So that's my x-intercept. Alright, let's put this graph together. Y-axis, x-axis. So I have a vertical asymptote at x equals 0. That's the y-axis basically. So here's my break in my graph. My horizontal asymptote is at a y value of 2. Okay. I have no y-intercept and I have an x-intercept of 1/2. Much like before, I'm going to say that my only option for my graph is to do this. As I approach the far end on the right, my graph has to approach my asymptote, so I would say it has to go like that. And my graph has two options from this point as I approach the vertical asymptote, to go up or to go down. I'd say up is not an option because it would have to bounce off this x-intercept, and this x-intercept has multiplicity 1, which is odd. Odd I have to cut through. So I would say that this is my only option to go down. Okay. Now I have no idea what happens on this other side over here, so that's where I'm going to need a checkpoint. So pick any number over here. -1. If I wanted to, say, find f of -1, okay, I would get 2 times -1 minus 1 over -1, which would give me what? -2, -1 is -3 over -1 is +3. So it gives me a point up here. Okay. So if my point's up there, then my graph is up there. This is where my graph is going to be located. Okay. I have to approach this vertical asymptote, and up's the only option. I can't go down because I can't cross the x-axis. A lot of people think you can't cross a horizontal asymptote. You can do that. You can cross a horizontal asymptote, but I can't go down because I can't cross the x-axis. I didn't find an x-intercept there. So this whole thing here is not an option. Oops. So on one end I have to point up over here by default. Right, and here I have to approach my horizontal asymptote, so I'm doing that as well. So this is what my rational function looks again. If you look at this example and you look at the previous example, they both have had similar shapes in that they have these catty corner curves to them. Here you get these catty corner curves. Whenever you have this shape, we call this shape a hyperbola. Okay. Which we'll discuss more when we talk about conic sections. Alright, here's another one. Rational function. Can't be simplified anymore. Numerator is just an x. Denominator is x squared minus x minus 2. I can factor the denominator as x, what would it be, minus 2 plus 1. But that doesn't help me simplify the fraction anymore. There's no factor that I can still cancel out of the numerator. So I go, alright, first step, vertical asymptote. Vertical asymptote, when is the denominator equal to 0? Well, when x minus 2 times x plus 1 equals 0, which is x equals 2 and x equals -1. There's two vertical asymptotes in this particular graph. There's no limit to the number of vertical asymptotes you can get. It all depends on how many zeros you have of your denominator. Horizontal asymptotes, however, the most you'll get is 1. 2, we're going to find that horizontal asymptote. Look at the degree. Numerator's a 1, denominator's a 2. Denominator's bigger, y equals 0. 3, y-intercepts. Find f of 0. Well, I get 0 over 0 squared minus 0 minus 2. So 0 over -2, that's 0. x-intercept. F of x equals 0. For this, numerator equals 0. That's my x-intercept. So y-intercept, x-intercept, horizontal asymptote, vertical asymptotes. So let's put this graph together. -1, vertical asymptote. +2, vertical asymptote. X-axis, horizontal asymptote. Y equals 0, x equals 0 is my x and y intercept. So now I got to start putting this graph together. Well, I have a lot of options now. Let's start in the middle. From this point, I can either go this way or this way as I approach that vertical asymptote. There's no way of determining which one without a checkpoint. So I need a checkpoint there. In that case, I'll use this number right here, which is a 1. So I'm going to find f of 1. Or, in this case, sorry, we have h. h of 1. In that case, I get 1 over 1 minus 1 minus 2, which is 1 over -2. So it's -1/2, so it's down here, which tells me that this top one isn't an option. Now, going the other way, option 1, option 2. Which one is it? We don't know. We need a checkpoint in here. In that case, that's going to be -1/2. So I have to find h of -1/2. Alright, well that's going to be -1/2 over 1/4 plus 1/2 minus 2. And I'm just plugging it into this original function here. Well, I get -1/2 over 1/4 and 1/2 is 3/4 minus 2. Now really all I care about is, do I get a positive y value or a negative y value? In this case, you can see that this denominator is going to be negative, this is negative, so overall this whole thing's positive. If I get a positive y value, I'm up here somewhere, which tells me that this bottom option couldn't happen. So just to make this clearer, my graph does this right now. Okay, it goes up here and down here. It approaches this vertical asymptote and this vertical asymptote. Alright, what about on this side and this side? We don't know what's happening here. More checkpoints are necessary. So you see this graph, we need a lot more checkpoints than other graphs. It all depends on how things set up. Alright, so let's look at some more checkpoints. So we need 2 of them, 1 on each side. So here, let's choose 3. Here we'll choose -2. So f of -2, or sorry, keep doing that, h of -2 is going to be -2 over 4 plus 2 minus 2, so this would be -1/2. So you get something down here. If I get something down there, my graph is down there, so it's going to look like this. Okay. And on the other end, I have to do h of 3. So it's going to be 3 over 9 minus 3 minus 2, so 3 over 4. That's positive. So I get something up here. Means my graph is up here. Okay, and that's what my graph's going to look like. Now this graph has 3 segments to it. Okay. Here my graph crosses the horizontal asymptote. Remember, my horizontal asymptote is the x-axis. My graph crosses the horizontal asymptote. That's fine. You can cross the horizontal asymptote. You can never cross a vertical asymptote. Okay? A vertical asymptote is a break in the graph. A horizontal asymptote is just the value you approach at the ends of the graph. In the middle, you can cross it. So that's what my graph looks like. Now this is not the best picture by far. I mean, if you really want to get an accurate picture, you can plug this function into your graphing calculator, you can plug it into a computer, but this is getting you the idea of what the behavior of the graph is and kind of how this function works from piece to piece, where the breaks are, whether it goes to positive or negative infinity. And that's really what you want to do. Just plugging this thing into your calculator and looking at the graph doesn't sort of give you the idea of why a lot of these things are happening. Alright, now that we've looked at a couple of rational functions, we need to talk about a third type of asymptote. Now, this third type of asymptote does not occur very often, but it is something that does happen with rational functions, so we need to discuss it. So the idea is slant asymptotes. Okay? And sometimes these slant asymptotes are called oblique asymptotes. Now, the general idea, if I can give you a general principle of kind of what's happening here, is you can think of it like your horizontal asymptote starts to tilt. And it no longer is a horizontal line, but a slanted line. And it will basically start pulling the graph with it, but only at the ends. Remember, the horizontal asymptote only determines what happens at the ends of the graph. And the slant asymptote is basically going to do the same thing. It's taking the horizontal asymptote and sort of starting to tilt it, and that becomes now a slanted line, which gives us that slant asymptote. Now, the only time that this is going to happen, the only time that you'll have a slant asymptote, is if the degree of the numerator is exactly 1 more than the degree of the denominator. If the degree of the numerator is 2 more or 3 more or 4 more, it's not going to be a slant. The slant asymptote will only occur if the degree of the numerator is exactly 1 degree bigger than the degree of the denominator. Now, if you think about that, when would you not have a horizontal asymptote? You would not have a horizontal asymptote when the degree of the numerator is bigger. So if we have a slant asymptote, we don't have a horizontal asymptote. Okay? And we'll only have a slant asymptote not only if the degree of the numerator is bigger, but exactly 1 degree bigger. So how can we find a slant asymptote? Well, let's look at this function right here first. Okay? So if you look at this function, the degree of the numerator is 2, the degree of the denominator is 1. So the degree of the numerator is bigger. If the degree of the numerator is bigger, that means there's no horizontal asymptote. And the second you have that, the next thing you should look for is there going to be a slant asymptote? Well, since the degree of the numerator is 2, and the degree of the denominator is 1, the degree of the numerator is 1 degree bigger, therefore there will be a slant asymptote. Okay. Now, how can we find that slant asymptote? So, in order to find that slant asymptote, we need to actually perform the division that we're seeing with this rational function. I mean, if the rational function is a polynomial divided by a polynomial, we already know how to do this actual division. So if we perform that division and we find the quotient, set y equal to the quotient, that line will be your slant asymptote. It doesn't matter if the remainder is 0 or not, and actually you don't want the remainder to be 0. Because if the remainder was 0, then that means that the numerator and denominator share a common factor. And again, we've talked about that a couple times now. We don't want that to happen. We still haven't decided or talked about what would happen if they have a common factor, but you don't want the remainder here to be 0. So if I perform this division, I can do it one of 2 ways. I can do synthetic division or long division, mainly because the denominator is in the form for synthetic division. So I'm going to use synthetic division. I'm going to put a 1 outside, a 1, a 1, and a 0 inside, because this one is missing that constant on the end, so I add like a plus 0 on the end for the constant. So I got a 1, and a 0. And this one I change the sign and put it out here. So I bring down my first term, multiply, place it here, add straight down, multiply again, place it here, add straight down. This is my remainder, this is my quotient. Again, we're not looking for the remainder to be 0. So if my quotient is x plus 2, then my slant asymptote is y equals x plus 2, and that's a line. So that line is the slant asymptote. That's going to determine what happens at the ends of the graph. Now, why are we doing this? Why are we looking at this for the slant asymptote? Well, it has something to do with this. If you look at the division we just did, x squared plus x divided by x minus 1. Okay, that's the function right here. So the solution is x plus 2, and we saw that there was a remainder of 2, so 2 over x minus 1, right? This is how we could write our answer. This thing over here is equal to this thing over here. Okay? If those two things are equal, then what I can do is say the behavior of this fraction should be the same as the behavior of this whole thing if they're equal. Well, look what would happen as x goes to infinity. Well, as x goes to infinity, if I look at this piece separately from this piece, as I look at this piece, I'm going to get x is going to get bigger and bigger and bigger. And if x gets larger and larger and larger, I'm then going to keep adding 2 to it, which means this whole thing right here is just going to keep getting bigger. On the other hand, if I look at this right here, as x gets bigger and bigger and bigger, the denominator of this fraction is going to get bigger. And if the denominator of your fraction gets larger, like say 2 over 10, 2 over 100, 2 over 1,000, if the denominator of your fraction gets bigger, the whole thing goes closer and closer to 0. So if this thing's going closer and closer to 0, then really as x goes to infinity, that's the right-hand side of my graph, I'm going to get closer and closer to whatever this thing is. And that's just a line, y equals x plus 2. Okay? Same thing happens on the other end. This thing's going to go to 0 right here, and we're going to get closer and closer to this line. So the slant asymptote describes what happens at the ends of the graph. Now how do you sort of put that into a graph? Well, you would do it the same way you would do anything else. So if we look at this function, it has a slant asymptote y equals x plus 2. You can see that the vertical asymptote is going to be x equals 1. So if I put those two things together, here's 1, this is my vertical asymptote. Y equals x plus 2 is the slant asymptote. So if I do a y-intercept of 2 and a slope of 1, so up 1 over 1, I get this line right here. And this is my slant asymptote. Okay? So what's going to happen is my graph, if I start plotting points and doing the things we were doing before, my graph's going to do this. Something like this. I mean, this is rough, but my graph's going to do something like this. And the idea is, as I get closer and closer to this vertical asymptote, like this, my graph's going to shoot up to that positive infinity or down to negative infinity. That's the same as before. But at the ends of my graph, here and here, my graph's going to approach this slanted line. Normally, that slanted line was a horizontal line, right? That's what we were looking at. And when it was a horizontal line, on the ends of the graph, I would be approaching that. But what happened is this slanted line is now getting tilted up. And if that slanted line is, if this horizontal line is getting tilted up, this whole function gets pulled up with it. So think about this. If I bent this line up a little bit more, a little bit more, a little bit more, the graph's going to curve with it till I get to here. So really what's happening is that sort of what happened with the horizontal asymptote is the same thing that's happening with the slant asymptote. On the ends you have to approach it, but now it's a slanted line instead of a horizontal line. Again, this asymptote doesn't occur very often, but you should still know how to find it and when it would occur. It's all about the degrees of the numerator and denominator. Alright, we have one more thing we need to discuss, and that last thing is, what if the numerators and denominators do have common factors? So this is the thing that I keep putting off and putting off for all this entire lesson. Now we're going to discuss it. Well, look at this example right here. This is a prime example of a function who numerator and denominator do have common factors. So what are you going to do? Well, generally you're going to do the same things we were doing all along with all the other ones, except you're going to simplify it first. You're going to cancel the common factors first. So if I look at this, you're going to have x minus 2 over x minus 2 times x plus 2. That's how you would factor the denominator. The numerator would cancel with the one factor in the denominator, and you're left with 1 over x plus 2. And essentially what you're going to do is you're going to graph this thing like you would all along. This thing right here has no common factors between the numerator and denominator, so the steps of graphing that are all the same. Find the horizontal asymptote, find the vertical asymptote, and go from there. But this graph right here is a little different than this original function that we were actually trying to graph. And it's different in that the original function had this factor in it. So what you're going to do is, after you graphed this function, the one that is already simplified, you're going to go back and say, well, what factors did I cancel out? In this case, I canceled out the x minus 2. When is that equal to 0? What are the zeros for that factor? In this case, x equals 2. What I'm going to do is I'm going to say, all right, well, this is something that would make the denominator 0. However, it's not going to be a vertical asymptote because I can cancel it out of the denominator. But it is still going to be a break in the graph. So I'm going to look at the final graph that I came up with for this function. Okay. In that case, if I just draw it real quick, it's going to have a vertical asymptote at -2, a horizontal asymptote at the x-axis, and it's going to look something like this. Okay. But that's the graph of this function. Okay. If I want to graph the original one, the difference is this right here. This one cannot be using an x value of 2, which means the x value 2 is going to be a break in the graph, but it's a different kind of break in the graph than a vertical asymptote, in that the break in the graph here is going to be what we call a hole. So I'll go, all right, here's 2. 2 would be this point right here, would have an x value of 2. That point right there is a point that I'm going to delete. So I'm going to look at this point, and I'm going to delete this point right here. So you delete it by essentially writing it as an open circle. And now that's what the graph of this first function looks like. The only difference between the graph of the first function and the graph of this last function over here is that hole. This last one doesn't have the hole, so if I started with that graph, I would graph the same thing I'm looking at right here. However, that's not really what function we wanted to graph. We wanted to graph this original function. Let's erase some of this. We wanted to graph this original function here. And the difference was this factor that I could cancel out. So what are you going to do again? You're going to look at the function. You're going to simplify it as much as possible. And you're going to get this function. You're going to graph the final function here that it's simplified, just like we did all along for the past couple of examples. Then you're going to go back and say, well, there was a factor that I canceled out. This is the factor that I canceled out. When was that factor going to be equal to 0? Whenever it's equal to 0, locate that spot on the graph, and in that case it's right here, and delete that point from the graph. So right now we have two different types of breaks in the graph we need to discuss. We talked about vertical asymptotes, which is a break in the graph right here, and it splits my graph into two pieces. And then there's also something called a hole in the graph, or what we call a removable discontinuity. And this hole in the graph is another break in the graph, because what's happened is my graph's going along here fine, and then it stops the second it gets to that point, and once it gets past that point, it starts again. So there's a break there, and that's why we put this open circle to show that that point is missing. Okay. Now this type of break in the graph here, this hole, is far less severe than the vertical asymptote, but they are two different types of breaks in the graph. Let me give you one more example. F of x equals x plus 2 times x plus 3 over x plus 2 times x minus 3. And I say, find the vertical asymptotes. Okay? So what a lot of people do is make a mistake here, and they'll just say, okay, whenever the denominator is 0, that's my vertical asymptotes. But remember, that was only a method of doing it if it was simplified. So if I'm going to find the vertical asymptotes, what I have to do is simplify first, cancel those factors, and now where the denominator is 0, which is only for this factor, that's where my vertical asymptotes are going to be. So when x minus 3 equals 0, that's going to be the only place I have a vertical asymptote, which will be when x equals 3. If I said find the holes in the graph, that would be for the factor that you canceled out. Well, the factor I canceled out is x plus 2. When's that going to be 0? When x equals -2. So that's going to be the hole in the graph. if I said, what's the domain? Well, the domain is anything I can plug into the function. Well, normally what we do is we say, well, what can't we plug in the function? What would make the denominator 0? Well, 3 would make the denominator 0, and -2 would make the denominator 0. This one occurs with a vertical asymptote, this one occurs with a hole, but they're both places where the denominator is 0. So the domain is everything but those two. So I could say all x except x equals -2 and x equals 3. That could be my domain. Okay? So what you can't do from this point on is when you're looking at a rational function and you're trying to find, say, the vertical asymptotes, to just set the denominator equal to 0 and solve. Because sometimes when the denominator is equal to 0, you'll also have a hole instead of a vertical asymptote. The only time you can set the denominator equal to 0 and say those are going to be my vertical asymptotes is if the fraction's already simplified. There's also a quick way to kind of look at it as well, and the quick way to look at it is if I find a place where my denominator is equal to 0, say 3, plug it into the numerator also. If I plug it into the numerator as well and I don't get 0, then that means there was no factor that could be canceled there. I mean, look at -2. If I plug -2 into the denominator, it's going to make this factor 0 and therefore make the whole thing 0. If I plug -2 in the numerator, it's going to make this factor 0 and therefore make the whole thing 0. So it would give me 0 over 0 when I plug it into the function. 0 over 0 tells me basically that it was a factor that could be canceled and therefore it's a whole. If I don't get 0 over 0, if I get some number over 0 when I plug this number into the original function, then it tells me it's a factor that couldn't have been canceled and therefore it's a vertical asymptote. So these are all different ways of looking at it, but it's something that you're going to have to be concerned with from now on. Most of the functions you're going to see right now are going to only have vertical asymptotes and not have holes. It's just the way the most pre-calc books go, is that they don't give you a whole lot of examples with the holes in the graph where there's factors that can be canceled. However, when you get to calculus, almost every example you're going to see for the first week or two will be all ones where you can cancel a factor out, and therefore they're all going to be the whole examples, the ones that have holes in them and have vertical asymptotes. So keep that in mind.